Okay, welcome everyone. So we are going to be working with 2 by 2 matrices and trying to find eigenvalues of 2 by 2 matrices when we can't factor the characteristic equation into two linear factors. So in other words, when the characteristic equation is a quadratic that cannot be solved with real numbers. So it's going to be worth it just to review some properties of quadratic equations. And these are going to be equations of the form ax squared plus bx plus c equals 0. And again, why we're interested in these quadratic equations is because if I want to find eigenvalues for a 2 by 2 matrix, it's going to require me to solve a quadratic equation. So if I have a quadratic equation, it's possible that I get two distinct real roots. So for example, the quadratic equation x squared minus x minus 6 equals 0. That has two distinct roots, 3 and minus 2, because this quadratic expression can be factored into the factor x minus 3 times x plus 2. So certainly with a quadratic equation, we could get two distinct real roots. It is possible that we get one repeated real root. So for example, if I have a quadratic equation, x squared minus 6x plus 9 equals 0, then this quadratic expression can be written as x minus 3 squared. So I have one factor with multiplicity 2. So that gives me one real root, x equals 3, that we say has multiplicity 2. And it's possible that we have no real solutions to a quadratic equation, in which case we're going to have two complex conjugate roots. And there's a nice picture that goes along with each of these cases. So for the case of two distinct real roots, that means we have a quadratic that might look like this and crosses the x-axis at two distinct points. One repeated root might be a quadratic that looks like this, where the vertex is right on the x-axis. And it's possible that if we're graphing a quadratic, we have a parabola which sits entirely above or below the x-axis, in which case we have two complex conjugate roots. So let's take a look at such an example. And so we encountered this when we were trying to find the eigenvalues for a 2 by 2 matrix. The resulting characteristic equation was lambda squared minus 6 lambda plus 13. So here I'm going to replace the lambdas with the x's, but the mathematics is the same. So if we want to solve this quadratic equation, it does not factor. So as before, we can use the quadratic formula, and the issue is the term underneath the square root in the quadratic formula is negative. So here I can see x is going to equal 6 plus or minus the square root of minus 16 over 2. And we've discussed that the square root of minus 16 we can write as the square root of 16 times the square root of minus 1. And since the square root of minus 1 is defined as I, we can take this minus 16 and rewrite it as 4i. So now I've got 6 plus or minus 4i all divided by 2. And it's really important here, what students might often forget is that you need to divide both of these terms in the numerator by 2. So this simplifies to 3 plus 2i and 3 minus 2i. So we would say that this quadratic equation has two complex roots, 3 plus 2i and 3 minus 2i. And these two complex numbers are complex conjugates of each other. So I'm going to explain what that term means on the next slide. Okay, so let's talk about some arithmetic that we can do with complex numbers. So let's say I've got two complex numbers, z1 and z2, where z1 is a plus bi and z2 is c plus di. Then if I want to add these two complex numbers, then what we do is we add the real parts together to determine what the real part of the sum will be, and we add the two complex parts, the imaginary parts, together to find out what the imaginary part of the sum is going to be. So I add a plus c, that's the real part. I add b plus d, and that is the imaginary part. So So we just add real parts and complex parts together. With multiplication, we would take z1 times z2, and we can distribute this product out as we would other similar looking products. So I have a times c plus ADI. And then I have CBI times BDI squared. And I squared, recall, is equal to -1. So I can then group all of these terms by the real parts and the imaginary parts. So for the real parts, I have AC and minus BD. So that's where this term comes from. And for the imaginary parts, we have AD plus BC times I. So multiplication is a little bit more complicated, but we're still defining it the same way that we define multiplication of numbers. We treat real and imaginary things as distinct terms. We have what we call the conjugate of a complex number that we denote with a bar over the complex number. So if z1 was a plus bi, then we would define z1 bar, the conjugate of z1, as a minus bi. So we keep the real part the same, and we change the sign of the imaginary part. And as a result of this definition, then we can see that the real part of the conjugate of z is going to be the same as the real part of z. So there's no difference, but the imaginary part of the conjugate of z is going to equal -1 times the imaginary part of z. And based on how we've defined multiplication and conjugate of a complex number, you can see that, first of all, if I take the conjugate of the conjugate, we get the original real complex number back. And secondly, if I take the product of the conjugate of z1 times the conjugate of z2, then that is equivalent to taking the product of z1 and z2 and then taking the conjugate of that. And there are lots more information about complex numbers and arithmetic of complex numbers and some geometry of complex numbers that are in the appendix. What I've presented here are really just like the greatest hits of complex numbers, the properties that we're going to need in order to continue our work with eigenvectors and eigenvalues when a matrix has complex eigenvalues.